Good.
All right. How's the connection? Can you hear me?
Good. Looks good.
All right, good. All right then. So let's continue. And before I do that, I want to remind everyone that there's exam next Wednesday, right? So this coming day after tomorrow, and so I'll be on Zoom again. And and as I said in my announcement, please log in into Zoom. I need to know that you are doing something, right? I have to report to people that I actually took care of them, and so please do that. And I'll be there. So if you have any questions or problems or something, just you can use chat or you can use audio. I will not be in my office. I'll be in my home because I don't expect too much of talking to do too much of talking. So it should be okay. And but nevertheless, I'll be right next to my computer and I'll be actually solving the same problems as you do. And so it's so so there is an open channel of communication. So you can, if you have any problems, you can ask. You don't need to ask me if you want to go to the bathroom, right? That's kind of questions you can decide on your own. And but anything else is you can do that. And but please log in. I will have to check that everyone is on Zoom. And if you're not, you'll have to have a very good explanation of that. All right. So before I continue. By the way, is there any questions about the exam procedure? Any questions? All right. Okay, good. By the way, please check that that time zones and stuff like that. It happens sometimes that time zone is wrong and you got wrong time and so forth. It happened to me with my daughter, so I know what I'm talking about. All right. Before I move on, I want to remind you of some notations which I'm using, and there are different ways how people do the notations in textbooks or whatever. What is more convenient depends on your preferences, depends on how you look at those things. But it's the same stuff. So, for example, for curl of some vector field, right? So the curl of a vector field A, which depends on R, it's a vector, right? Depends on position R. So I use a notation. This means that equivalent. That sign means equivalent, which is that nabla vector, right? Vector of operator and cross A. That's completely equivalent, right? I like it because that operator is just partial derivative d over dx, d over dy, and d over dz, right? So then what I do here, I just use standard vector notation. So this is a cross product of two vectors, this vector and vector A. And after you do the cross product, those operators must act on whatever the components of vector A they come together, right? So in this sense, that makes it much less stuff to remember, because now this is my curl and the divergence of a vector, as I've used many times already. The divergence of a vector, divergence if of vector field A is just the same kind of notation. It's just a dot product of the same operator with vector A, and in gradient of some function, right? This is scalar function of all coordinates with the same notation. It's a vector acting on a scalar, right? So you see that it sort of makes it uniform, and I don't need to remember a lot of things this way. There's one more operator which is commonly used in physics and mathematics. It's called Laplacian operator. It's written like this. It's the same sign but inverted. when acting on some function f, doesn't matter what this function, it can be vector or function. And what it means is the same vector operator, dot product with itself, and then it's act on f. Right. In components, what it means is that this is second derivatives, because this is two operators acting, so it must be second derivative over x squared plus d to f over dy squared plus d to f over dz squared. So those things are just equivalent notations of the same thing. I always find that this I use for Laplacian operator. I usually use this sign, and for everything else, I usually use those ones. So it makes it a little bit easier to remember which one is which. Plus, it does have some sort of some additional information. The notation itself shows you some additional information. It tells you the curl of a vector field is a vector field, right? So when you take A and you cross product it with something, right? When you cross product two vectors, you got a vector, right? So what it means is that when I do this here, I get a vector field, and I can write it in components. Like, so for example, if I say that I have this vector field and its x component, right? It's a vector field, so it has x, y, and z components, and its x component will be dAz over dy minus dAy over dz. This is exactly the rules of the vector product, of the cross product of two vectors. So it has x component, z component, and y component, and they behave as vectors. So and that's visible from here, because I remember very well that cross product of two vectors is always a vector. All right, so that means that curl of a vector field is a vector field, and divergence is this is dot product, right? So a dot product of two vectors is always a scalar. So the dot product of two, so it means the divergence of a vector field is a scalar field. It has no components; it's just number field, and so forth. So and here again, I look at this. This is a scalar. This is a vector, right? That operator. So gradient of a scalar field then becomes a vector field, and so it has this information of what I get at the end. So that's why I like those notations better than those writing in letters, and I will use those ones. All right, is it clear?
Yeah.
All right, good.
When you have the Laplace written there, are those partial derivatives or full derivatives?
Those are always partial derivatives.
Okay, thank you.
So we're only concerned about the you said a full derivative means that some coordinates depend on each other. No, we see that we think the field, right? So it's a full space, and on each point there is a vector, right? This vector is in each point is its own vector. So we can ask how that vector changes when it moves from one point to another. So that's what it does. So we only move points completely independent from each other, but that means partial derivatives. All right.
Okay, thank you.
So it's a good question, but it's a nature of definition of a field. If those I only can move along some path, then it's not really a vector field. It's a vector field on the path, and I need to take care of that, and it's a different story. It's actually the whole branch of mathematics is dealing with those things. So it's not a trivial question, but thank you for asking it. It's a partial derivative. All right, so that's just notations, and I will use them, and I wrote them on my lecture notes. So if you're unsure what any notation mean, and you are more familiar with the curl and divergence and so forth, then you can use my notes and translate one to another. They're completely equivalent. There is no real difference between those things. All right, so let's continue then and write down what we already know, right? What we figured out last lecture. And last lecture, what we were dealing with is the Gauss laws for both electric and magnetic field, and they look almost the same. So the Gauss law in electric field tells you that if you have some region of space, right, then if you take the boundary of that space, the surface of that region, and you take that, this is the surface of that region, the region is omega, and you take electric field and you compute the flux of electric field through this surface, then what you will get is it's 1 over epsilon naught times the total charge inside this volume. Okay, so this is Gauss law for electric field, and for magnetic field is exactly the same. The only difference is that there is no magnetic charges. So it means that for magnetic field, the same law reads that the flux of magnetic field through any closed surface, right? This is always closed surface, the boundary, is always 0. Because it's exactly the same law, we just substitute 0 here, and then the integral of 0 is 0. And so that's Gauss law in its global form, and we of course can rewrite it as a local forms, and the local version of the same laws will read as okay, let me write it here. So local version of the Gauss law for electric field is the divergence of electric field, and at every point, right, equals to 1 over epsilon naught times the density of charge at the same point. So that's why it is, I call it local version, because it's always dealing with just one point or small neighborhood of one point, if you think of derivative of property of neighborhoods. And the same thing is for magnetic field, just tells you the divergence of magnetic field is always 0. Again, the same thing is that the density of magnetic charges is always 0. So it's basically the same law with that restriction on magnetic charges, right? Is it familiar? That was last lecture.
Yeah.
So now I want to emphasize something which always gets lost, and when we teach the physics, to introductory physics especially. Those are laws which you used in introductory physics. The Gauss law, it's exactly the same. It may be written a little bit more elaborate, but it's this way is actually easier to use because we know what to do, right? Remember that all integrals tell you what to do. You take the surface, you split it on tiles, you compute the E dot ds on each tile, and you sum them over. And so forth. That's what this tells you what to do. And this tells you just to compute the total charge inside this volume. So it's exactly the same laws as what you studied in introductory classes. What I want to emphasize though is that remember I use those laws, that global version of those laws. For example, to compute electric field due to a charged wire. So you have wire with a charge, infinite wire with uniform charge on it, and then we find out that the electric field goes like 1 over r because of the symmetry. And at this point, I used the following surface, right? It was a cylinder of radius r and length l. Now, I want to emphasize a very, very important point in those things. This law does not care what kind of surface or what kind of volume you use. It will always be correct, no matter what. So it means that if I have the same wire, for example, and instead of this cylinder, I would use the sphere like this. This law written for that volume will also hold, right? It will hold for any surface whatsoever, for any volume. Doesn't really matter what you do. It will always be true. It's independent of what kind of volume you use, right? But then you should ask why am I using that cylinder here? And the only reason for that is that I know what I want. I want to find out what electric field is here, right? And but this is integral. It's the sum of all electric fields. So if I try to use it here, you see that, for example, let's take this tile. It has area pointing out, right, at some angle, and the electric field here, as we know from the symmetry, is pointing this way. Right. So now I need to take that between those two, and some over the tiles. And if I do it this way, there is no way for me to extract electric field out of this integral. Simply because I will have some integral and I will not know what to do with that. I don't know what it is because I don't know electric field, how electric field depends on R. Right? That's what I want to find. But if I choose this particular surface, so this particular volume, the cylinder, then actually using the symmetry, I can actually take this integral without really knowing what electric field is. And then from that equation gives me how electric field depends on the distance. Okay, does that make sense?
Yeah.
So the law is correct for any surface whatsoever. There is no restriction here. It's always correct. This is exactly the reason why this formulation and this formulation are equivalent to each other. Because it's correct for any volume. But which volume I choose, it depends on me. That's sort of smart people thought about it, and they figure out that if I choose this particular volume, then I actually can solve the problem. So that's where you use your brains to choose the surface which will allow you to solve the problem. Now, so you can imagine that if I have some arbitrary distribution of charges, then there will be no such surface which will allow me to extract electric field out of the global version of the Gauss law. It just doesn't exist, such surface. I always will have some sort of integral, and I will not know what to do with that because there is not enough symmetry in the problem with arbitrary distribution of charges. And then what I do, I actually can use this law, which is local law. And if I know how my charges are distributed in space, I treat it as a differential equation, and I need boundary conditions for those differential equations, and then I can solve it. It's a differential equation of the same first order, but it's actually, well, it's one equation for three functions. But it's possible with knowing boundary conditions, I can actually solve it. And well, if I can, right? Mathematicians told me that I always can. All right, so then it means that I can. Right. How to do that? It's a different story. All right, so that's the nature of those laws. They're very general in this sense, and how you use them, that's a different story. All right, but I also want to point out that those laws. Well, let's remember that those two formulations are completely equivalent to each other. So I want to concentrate on those ones for now, because they are differential equations, and we know a lot about differential equations. And what I see here is that this is electric field, this is magnetic field. Those are vectors. Each vector has three components. Each component depends on all the coordinates, right? So what I have here is actually 6 unknown functions. 3 components for vector E and 3 components for vector B. So I have 6 unknown functions and only 2 equations. Remember that divergence is a scalar field. So those are scalar equations. And what I have is 2 scalar equations, 2 equations for 6 fields, right? For 6 functions. Well, that's definitely not enough. All right, it's I don't have enough equations for the fields. But that's not the only problem here. The other problem is that those equations do not have time derivatives. This is only space derivatives, right? So those equations do not tell me how electric and magnetic field changes with time. Sure, if I change the density with respect to time, if I change the density of, I move charges, right? So I change density of charge as function of time. Then of course there will be some effects on electric field, and it actually will be translated right to the change of the electric field. But it tells me that the only way to change electric field is to move charges around, which is not actually correct. And the experiment shows that it's not so. But that equation does not have, so this equation does not have the dynamics of electric field itself. And this equation actually doesn't have anything at all. And so in this sense, that's not clear what the sources of magnetic field are, right? Because it's 0 all the time. So B equals 0 is always a solution, right? But we know that magnetic field sometimes is not 0. So there must be some sources of magnetic field. So those equations in this sense are definitely not enough. We need more. of those. And that's and there are, of course, it's the total number of equations is 4, written in terms of electric and magnetic field, and and that's what we're going to do today, to develop the other 2 equations. Okay, does that make sense?
Yes.
So,
Yeah.
all right. So the series so far is not complete. We need to complete it. We need to find some other equations. And of course, you cannot find equations just by looking at some mathematical formulas. You have to do experiments. All right. And people have done those experiments. Fortunately for us, all those experiments been done, and people studied that very, very hard. What is the sources of electric field? What is the sources of magnetic field? How they connect with each other? They had a lot of experimental data. They analyzed that data, and they tried to figure out what is the simplest theory which will describe all the data. And it was done, and so we now know it. And that's exactly what. So I'm giving you just the final result of those, right? So you have to understand that. I think I already told you that when you study like physics or any science in reality, and you know that like there is some laws like Newton's law, like Einstein's law, and blah blah blah. All you study in this case, if you're trying to figure out what the history of science is, all you're studying is the success stories. Those are people who actually finally figured that out. But there are a lot of very, very smart people who had very interesting ideas. Those ideas just didn't work out. They had some ideas, they developed it in the hypothesis, that they find out what is the consequence of this hypothesis must be. Then they checked it on experiment, and it was wrong. Right, so the idea has to be discarded, but people already spent 30 years of their lives doing it. It's a standard story, and a lot of smart people were working on it. But on the other hand, the success is impossible without those failures, right? Because if you don't have those failures, you don't know where you should not look. Right, and you will repeat in the same. People would be repeating the same mistake over and over and over again, and there will be no progress. So those unsuccessful, the stories of failures are as important as the stories of success. In fact, but they never studied in any physics classes, and I'm very much afraid that the general population thinks that the scientists just go there and they figure things out. Well, 99% of the time we go there and we try to figure things out, it is wrong. We made a mistake, or the idea is just incorrect. It's not a mistake, it's just things do not work the way we thought that they would. So, but without that work which didn't lead into successful theory, without that work, the progress is impossible. So it's that's why the development of science is so expensive. It requires a lot of wasted work. And by the way, it's not always wasted. Some ideas which were discarded a long time ago come back later on in a completely different level and so forth. For example, there is one idea I actually liked it a lot. So when people didn't know what atom is and how it's constructed, now we know it and we can measure a lot of things about atoms. But before we could measure them, people didn't know that. And one of the ideas were that the question was why there are only some specific atoms, right? Some specific elements, chemical elements in the universe. Why it's not distributed completely continuously? And the idea was that every atom is just a knot of some sort of a wire, right? And so there are different knots, and there are not that many of them if you consider only simple knots. And so those knots are like the atoms are just knots on some wire, and we can describe them and classify them this way. And it actually worked for some of the elements, but not for all of them. And so the idea was discarded. But now it actually came back with the string theories because they're very similar idea actually important there. So it's very interesting how people think about it and what kind of crazy stuff they come up, and eventually they come up with stuff which is so crazy that it actually works. and we'll talk about it a little more later. All right, so but now I want to just do this complete the electrodynamics equations of electrodynamics, and those equations which I will write eventually are called Maxwell equations. And again, they were developed through very many years, with many tries, and then a lot of people worked on them. And eventually Maxwell was able to formulate them in the simplest possible way. All right, so before I start, I need to introduce now another mathematical construction, which we will be dealing with during this lecture. And that mathematical construction is the following. Let's imagine that I have a vector field, right? So some arbitrary vector field. So on each point of space I have a vector. That's it. That's all I know. And the only thing which I require is that vector field is smooth. So when I go from one point to very near to a point which is very near to that one, that field does not change too much. Right? So it also changes by just a little. So I can differentiate those fields and so forth. It's a smooth field. So I have that field everywhere, right? So every point of space has a vector. So I put a point somewhere in the space and it has a vector in there. Then what I draw here arbitrary path. It's completely arbitrary. And I say that this path goes from point A to point B. And I say that it's going from point A to point B. So it has orientation, right? It has a direction. It goes from point A to point B. And then what I can do, I can take my field, right, and construct the following property. Right? And it goes from point A to point B along the path gamma. So I call this path gamma, it's a gamma. All right? So that's exactly the same story as the work. Remember that if that vector field was a force, then this dr is my change of my coordinates. Then what this integral gives me is a work which that force will do when the particle moves from point A to point B. Right? Remember that?
Yeah.
So that's exactly the same thing, and it's that construction which I want to consider. But now I want to consider only closed loops. So I will say that my loop is actually closed like this. So it's still some gamma. All right. Now it's written like this. So that emphasizes that the gamma must be a closed loop. Now I draw it everything on a blackboard, right, on a flat surface. But that nothing here is supposed to be flat. So that vector A can be sticking out, right? I mean, it's arbitrary vector field, so it's not restricted to be in this plane. It sticks in all the directions, and that loop also that does not have to be a flat loop. It can go here, then go up, then go down, then go again here, and so forth. So any loop whatsoever. This is just a construction, right? So it has no meaning. I'm just saying that I want to consider this construction. And the path gamma is completely arbitrary, and the vector field is given to me. Okay, does it make sense so far?
Yeah.
So when I have this construction, it has its own name, and it's called circulation. It's called circulation of vector A, field A over path gamma. Right, and the reason for that is it's very simple. So let me give you some example. So let's imagine that my vector field is just a constant vector field. So that vector A is the same in every point. Absolutely the same, right? And then I can choose my gamma. Well, it's up to me what to choose. So I can choose it this way. I can say that this is my path gamma. I have to give it an orientation, right? I have to tell you which way I'm going around, this way or this way. The answer doesn't have to be the same, and it generally is not. So let me give that orientation like this. Right? A typical default orientation is when people use it, the counterclockwise. That's when they draw pictures. So now I can sort of compute that, and what I see is that when I'm going around this part of that loop, every time my dr, which is this little vector, right? Every time my dr will be perpendicular to vector a at every point. And so when I have dot product of two vectors which are orthogonal to each other, I get 0. So from this part of the loop and from this part of the loop, I have exactly 0 contribution. Right? And from this part of the loop, I have some contribution. But then I have another contribution from this part of the loop. And if that field A is the same here and here, then you see that every dr here on this part is the same direction as the vector A. So it comes with plus sign, right? Its dot product is just the product of A and the magnitude of A and dr. But here they always will be the opposite ways to each other, and that gives me minus sign. Right? But because the vector A is here and here, the magnitude is the same, and the length is the same, then it means that I will always have 0 here. Right? So that the contribution from this side will always be compensated by this side. So the circulation then of that vector field, of the constant vector field, over actually arbitrary loop, because for any loop I can actually split it in small loops like that and compute it. For any arbitrary loop will be 0. Right? On the other hand, if you consider different vector field, say like this one. So I have some point, and then vector field is actually twists around this point like this. Right? So it goes around, circulates around that one specific point. You've seen such vector fields in your bathtub, right? When water goes down the drain, it starts to spin around, right? And if you now look at this at one particular point of time, and in each point of space, you will have a vector of velocity of water at this space, at this point, right? So so you have a vector field of velocity. And if you look at that now, that's how it looks like, right? It goes around of a drain. So, right? So that's your bathtub. So now if you do the same construction and you choose some loop, for example, this one, right? Then you see that everywhere. Well, I chose it in such a way. Let's say that loop is oriented this way. Then on every point, what I have is that negative. That dot product will be negative, right? So when I sum them up, it will be sum of bunch of negative numbers, and sum of bunch of negative numbers will give me a negative number which is not 0. So that in this case, the circulation of that field A is non-zero, and you see that it sort of circulates around, right? So that's why it's called circulation, because it sort of tells you what there is a twist in your vector field, right? So it twists around, right? So it's not necessarily, it's not that easy. I mean, there are plenty of cases when if you look at that, you don't see the twist, but the circulation is not 0, and I think I will have it on next homework, such examples. But nevertheless, it tells you that something is not really that easy, and something is twisting around. So anyway, that's a completely mathematical construction. So far it has no physical meaning whatsoever, no content. It just says that let's consider this construction. It's called the circulation. So what's important that mathematicians did consider that construction, and they figure out that there is a special theorem about the circulation, which actually has the same flavor as a Gauss theorem, which we studied before. And moreover, in some language, it is exactly the same as Gauss theorem, but it's language of differential forms, which I don't want to go into. So in standard vector calculus, that theorem is called the Stokes theorem, and it tells you the following story. So quite an interesting story if you think about it. And the story is the following. Let's imagine that we have any particular path, gamma, right? Again, it doesn't have to be flat. Remember that I'm drawing flat because I just cannot draw in 3 dimensions, but it can be any path. But now it's a closed path, and we can consider that closed path as if we have some surface here. Let's call it sigma, and that path is just the boundary of that surface, right? Does that make sense?
Yes.
All right. So just a second. I need to increase volume. You can try to hear you. All right. So this is a boundary. So now my path is a boundary, right? I need to choose orientation. This definition requires me to choose the orientation of gamma. Otherwise, I don't know where the point dr is pointing. So if I have just a path and then I can take a little piece of it, I don't know which ways my little dr should point to, this way or that way, right? And every time I don't know something, it means that the definition is not complete. I have to be able to tell precisely where it points. And so if I choose the global orientation of my path gamma, that in every point I will know what the orientation of dr is. In this particular case, this is this orientation, right? Because it has the same direction of my orientation of my path. So that definition actually requires me to have an orientation of my path. So I need to choose that orientation somehow here. And so I choose it arbitrarily. I say that, okay, well, this is my orientation. That's fine. What I will later on need to do is also orientation of my surface sigma. Remember that orientation is what for the surface? I take the little piece here. It has some area. It's flat piece, right? It's very small, so it's flat. It has area, and the vector of area is sticking perpendicular to that surface. But it can stick either towards away from the blackboard or into the blackboard, and it will still be perpendicular, right? Right?
Yeah.
Yeah. Doesn't that depend on orientation in this case?
Yeah. So I need to define which way I want it to be, and so I define the orientation of all the little pieces using my right hand. It's always right hand. All right. Always. Don't mix it up. So I take my fingers, which go around this loop, right, like this, and then my thumb is showing me the orientation of all that little ds. Right. So in this particular case, the ds is going this way. But you can do that. You can understand that you can do that for any kind of path, right? If it's not flat, then what is required is that it's sort of the same orientation everywhere. Right, so you choose the orientation in such a way that it never switches too much. The orientation by itself should be a smooth vector. So you choose it at one point, and then you can always continue it to all other points of your surface, if the surface is orientable, which is not necessarily so. But we only consider those cases. All right, so that's the way. That's a convention. There is nothing particular special about right hand. We could have done everything with using our left hand, right? And everything would go through exactly the same as now, except some formulas will get the minus signs, extra minus signs. But some will have, instead of minus, will have pluses. So we will just switch signs in a bunch of formulas. And at the end of the day, when we talk about something which we measure, right? That the result of the measurement must not depend on how we define which hand we use, right and or left, and it will not. Right, so we can use everything in left hand using left hand and write all the formulas, and we'll still get exactly the same answer for everything which we measure. There's no problem with that. So then it's just a matter of convention, how people write the formulas. So when you look at the formulas, you must be able to tell what it is, right, and what convention has been used. And since already 300 years, people always use right hand to do that, and all formulas which you ever see in any textbooks will always use right hand convention. So that's the convention. You just use it like this, and then that's orientation of sigma. So then I can write this for any vector field, smooth vector field. I can now define the circulation around the boundary of that surface sigma, piece of surface sigma, and the theorem, which is called Stokes theorem, and it's in reality just the reformulation of Gauss theorem, blah blah blah. And it tells me that that's equal to the integral over total of the whole sigma, and the integral of the following object. I need to take a curl of my vector A and integrate and dot product it with the vector of area. Okay. So what it tells them now, let's discuss left hand side and right hand side again. Left hand side is what I do. I take the boundary of some piece of surface. I choose an orientation for the boundary. I split it on little pieces, right? For each little piece, I have dr, right? And for each little piece, I have dr. And on each little piece, I have vector A here. And now I take that vector dr, I take the product, the dot product of this vector A, it's what's written here, right? And then I sum it over all those little drs around the whole loop, right? That make sense?
Yeah.
Can you say what A is again in this case? Is that just an arbitrary vector?
Vector field. Doesn't matter.
Okay. A vector field, though, not just a single vector?
No, it's a field. It's in every point they have different value, different orientation, different magnitude.
Okay.
The only requirement is that it's sort of smooth. It's not jump. It doesn't jump. It's not like it is here up and right in the next point it is already pointing to completely arbitrary direction. It changes smoothly. And the right definition of what does it mean smooth, it means that the derivative exists, the next derivative no exist, and so forth. Let's forget about those things. Intuition is enough here. So that for any vector field it is so. So for any vector field, then I can do that construction. It's exactly the same construction as for work. When vector field was a force, right? That was a work around the closed loop. When we move around the closed loop. Now this is the left hand side. The right hand side is a completely different story. The right hand side, I need to consider the whole surface as the first surface sigma. I need to split it on little tiles. Now, I need to split it on little tiles. Each tile will have vector ds, right? And that vector ds is its magnitude, is the area of that little tile, and the direction is perpendicular to that little tile, and that direction is where it goes from the blackboard to the blackboard is defined by the orientation of my path. Of the orientation of my path d sigma. So I use my right hand side. So that's the vector which I define on each for each tile. I take this vector. I take the values I take the field A at the very same point. I take the cross product, right? I take the curl of the I take the curl of the vector field at each point here, right? It's another vector field. It's another vector. It's a curl. And I take the curl and I dot product. It is my vector ds, and I sum it over all tiles. That makes sense?
So you're turning a line integral into an integral of the surface.
Yes, yeah. But you see that this is line integral of a vector. Let's take another look at it. This is line integral of the vector field A. All right. But this is what is written here is the flux of this vector field through the surface, through the full surface. Okay? That makes sense?
Yeah.
All right. Good. Now, it should be very surprising. That formula actually correct. Remember that it's for any for any piece of surface sigma and any smooth vector field, this will be correct. It's called Stokes theorem. You can check Wikipedia if you want. And this is very surprising because you see that the left-hand construction, this construction, knows about that field only on the path, on the boundary, right? This is the only field, the only points which I use here in this construction, right? So it knows, that construction knows nothing about what's going outside of that little pair. Now, on the other hand, right-hand side, I'm taking the integral over surface, so I have to take the curl of that vector field and compute it in every point of that surface. So somehow that construction will know something about the properties of my vector field inside on the surface.
Well, this is just the conservation law, isn't it?
No, it's not. There is no conservation laws is a physical statement. There is no physics here. It's a theorem. For any vector field, it is so. That's it. All right? So but it's the same thing as a Gauss theorem. Remember that Gauss theorem connects the integration over the flux of some vector field through closed surface with the integral of a divergence of that vector field inside that volume. Right? We discussed it last lecture, and I showed that it's not as surprising because there is a simple example of it, and it's just your standard integration of a derivative. So that was last lecture. That has the same flavor. But here there is one more thing which should be surprising. Imagine that I have some path like this. Right? Now I can actually do different surfaces which have this path as a boundary. So one surface is this one, right? So it's just little cap. But the other surface, well, let's call it some other cap like this, but smaller. Those two surfaces have exactly the same boundary. So ds is the d sigma is exactly the same for them, right? So if I now use that in this construction, those two surfaces, the left-hand side will be exactly the same for both of them, right?
Right.
Yeah.
Because that field has exactly the same values, and that boundary is exactly the same for both surfaces. Okay? So let me call this surface sigma 1 and this surface sigma 2. The larger one. Then what I have, is that what that's what I used. So you see that from this construction, what I have here, that d sigma 1 equals to d sigma 2. Right? So what it tells you is that boundary of this surface is the same as boundary of this surface. There is no differentiation here. Remember, this is just notation for the boundary. So boundary of this surface equals to the boundary of this surface. Right? So, but that's exactly how I constructed it. But if it is so that this integral, I don't actually have this surface here. So I can just compute this integral knowing just the boundary. This is the left-hand side. Now I go to the right-hand side and I see that in one case, I need to use sigma 1. On the other case, I need to use sigma 2 here. And somehow, the answer must be exactly the same for sigma 1 and sigma 2. For two surfaces, I must have exactly the same answer here from the right-hand side. Right? Otherwise, the theorem doesn't make sense. Do you understand what's the problem?
Yeah.
Right.
I'm sorry. Do you understand or not?
Yeah, that makes sense.
So you see that I can choose two different surfaces. They will have the same boundary, but the surfaces themselves will be different. So this integral will be exactly the same for both of them, but this integral, it depends on the surface which I choose. Where do I put my tiles? This surface or the other one? So if you look at that, this integral does depend on which surface I choose. And in this case, I either have to choose a surface in very specific way, right? And then this theorem is not really interesting. Or it must, that the right-hand side must not depend on which surface I use. And of course, because that's a theorem and I'm talking about it, what actually surprising thing is that this integral does not depend on which surface I use. I can choose whatever I want. The integral will still be the same. So let me prove it to you. This proof I will use later on in physical content. So it's the same construction. So I will show it for the arbitrary field first. So let's now look at this situation, right? So let's imagine that this is our orientation of our boundary, right? This is boundary d sigma. And so the orientation of sigma 2 is this way, right? The orientation of sigma 1 is going this way. Okay? That makes sense? Now, let me now look at this the following way. Let me look at this integral, right? And write it the following way, that it's integral of curl of vector of A ds taken over sigma 2, right? Okay, so it's a dot product. And the second one is the same integral, but taken in sigma 1. And I want to prove that they're the same. So what I want to prove is that if I take the difference between those two integrals, one over sigma 2, the other is over the surface sigma 1 of curl A dot ds, right? That this must be equal to 0. If I prove that, then it means that the integral does not depend on which surface I take, as long as those surfaces have the same boundary. Right? That makes sense?
Can you explain again what you mean by having the same boundary?
The surface has a boundary, right?
Yes.
Two surfaces can have the same boundary.
I'm not sure I understand that.
I really don't know how to explain it. So let's imagine that this is my boundary, right?
Okay. Yeah.
So here's one surface, right? So it's a surface, right? It's a cap.
Okay. It's like a cone sort of a thing, or a
cap,
dome.
right? Like this, just staying on there.
Okay.
Here's another surface.
Okay. And so it's a different surface, but it has that same in the XY plane.
Boundary, but they're completely different surfaces.
Okay, that makes sense.
All right. Good. So it's a. Sorry, my drawing probably not that spectacular, but really it's the best I can do. So what it tells me is that theorem tells me that this integral must not depend on which surface I take, as long as the surface has the same boundary. Otherwise, it makes no sense. So it means that if I consider now this integral over one surface and the other surface, the difference between them must be 0. So it means that this integral has exactly the same value as this one for two arbitrary surfaces. Okay? Does that make sense? And somehow this statement must involve the fact that both of those surfaces have the same boundary. Right? Because if they don't have the same boundary, then this statement is not true. So here's the story, right? Consider two surfaces which have the same boundary. Because they have the same boundary, they actually enclose, they together, they make a closed surface. Right? So this is one boundary, this is one surface, this is another surface, and they have the same boundary. So you see that they construct the total surface. Closed surface, right?
Yeah.
That's exactly the statement that they have the same boundary. So I take two surfaces and I glued the boundary together, right? Then of course that's it. That there's nothing else. I have the closed surface. Okay. Now there is also orientation. The problem for orientation. Remember that when I have a closed surface, my convention for orientation was always that the vector of area is pointing out. Right? If I do it here, and I think of surfaces as having their own orientation, right? You see that this vector of area is pointing out, but this vector of area is pointing inside the volume, right? So I need to switch it in order to have the integral over the total surface. But switching it means that all the integrals around the surface sigma 1 must be multiplied by minus 1. Right? Does that make sense? So what it means that this actually equals to the integral, right? Now I need to switch the integration here, and then what the sign here, and then what I have is just a plus sign. So I have curl of vector A integrated over total surface of the total surface, right? The full one of them. So I can write it sigma 1 union with sigma 2. So don't get scared about that notation. It just means one surface and another surface. That's it. But now they have orientation so that the vector ds pointing out all the time. Okay? Does that make sense?
Yeah. Yes.
Okay.
Yes.
But now we see that this is a total flux through the whole closed surface. And for that integral, I have Gauss theorem, which tells me that it must be equal to the integral over the whole volume, which is inside of those two surfaces, this volume inside it, right? Let's call it omega, of the divergence of that field. Right? This is Gauss theorem. Okay? That makes sense? But you see that this is divergence of a curve. And this is always 0. Right? Just as with vector products. So this is always 0. And the integral for 0 is 0. That's exactly the 0 which I want to get. Okay? So what turns out that because of the Gauss theorem, which again is, remember that Gauss theorem is correct for any vector field, including that vector field. Any means any, whatever. This is a vector field. So because of the Gauss theorem, this always correct, and it doesn't matter which sigma I will choose. Okay? That makes sense?
Yes.
Yeah, let me real quick show how that can be used to prove something which we have proven before. And so let's consider work over the closed path. So we have some vector field force F dr, right? And it's a closed, and we move particle over some closed path, right? So this is the work which needs to be done, which force is doing during that motion, right? So again, but this is exactly the same construction as here. The only thing which I need to consider is the surface which has gamma as its boundary. All right, so let me call this surface sigma. This is d sigma here. All right, this is a work over force. And according to this theorem, it equals to the integral over sigma of curl f dot ds. Right? That's just the same theorem as here, the same written as here. So now I see that if curl of f, if it so happens that my force field has a curl of curl 0, right? Then this will be 0 all the time. And then the work over any closed path will be 0. But that's exactly the requirements that my force is a gradient of some other of some potential energy, right? Because if force equals to gradient of the potential energy minus gradient of potential energy, then what I have is minus, and here I have again two vectors of the same vectors, and that vector product is always 0. Okay. So for any potential force, then for any force which satisfies this requirement, the work around any closed path is actually equal 0. You see, it's much easier to prove those theorems using that Stokes theorem. Okay? See, it's just one line, right? And we spent about half a lecture on it last time. That makes sense?
Yeah.
All right. Now, the good question would be, what does it have to do with electric and magnetic fields? Well, those are vector fields, right? So we can see what this construction means for them, for those vector fields. Now, I want to put some, again, this is just a theorem. It tells me that this left-hand side equals right-hand side for any vector field, any sigma, right? It's really not, it has no physical content whatsoever. It just tells me something about those mathematical constructions. I now want to use it for mathematical, for physics. And for that, I need, of course, some physical input. Something about my world. That construction, that theorem knows nothing about what kind of world I live in. I don't even know it myself. So it just tells me that one construction equals the other. That's it. Now, so we need to do some experiments to figure out what kind of laws we have, blah blah blah, all this stuff. It has been done, of course, and you know all of this. And the first law which I want to discuss is called Faraday's law, and you probably have you should know that already, and you're familiar with that in the following form: that if you have a loop of wire, and you put magnetic field through that loop, you see closed path, flux of the magnetic field. You see that it's very close, right? So then you have in this situation there is electromotive force inside that wire, and that electromotive force equals minus dF b over dt, right? Whereas this dF, this F is the flux of the magnetic field through this wire, through this loop, right? And then this is the rate of change of the flux. You know this, right?
Right.
All right. So this is called Faraday's law. It's very strange written like that. Because what does wire has to do with that? So how comes that law, which in the right hand side has completely something which can be defined anywhere, right? It's a flux of a magnetic field through some surface, and yet we need to have a wire here. That's ridiculous, right? So we don't. In order to understand why we don't, we need to understand what that electromotive force is. And electromotive force is exactly the work which needs to be done in order to move a charge around this loop. But the work which needs to be done in order to move the charge around the loop equals electric field times dr, right, over the path gamma. This is now my path gamma, and this is exactly what work is. I need to take test charge q, little q, multiply it by q, right? Then this is the force, right? And this is the force times dr, so it's work. So it's exactly the work which is done can be done by moving charge around this loop. But now in this formulation, so this is my EDS. This is EMF. This is electromotive force, right? So it knows nothing about the wire anymore. It's just the property of electric field. Okay. And now what this law is stating, that this, if I now consider this surface, right, then this gamma is the boundary of my surface, and let's call that surface again sigma. So this is d sigma. This is my electromotive force. And what is written here is that electromotive force must be equal to minus integral of B dot ds over sigma. And then I need to take the time derivative of it with the minus sign. Right? You see that this is now exactly the same as this. This is the flux of magnetic field, right? And this is my electromotive force. Does that make sense?
Yeah.
So you see that, but now you see that this, in this formulation, this the whole story doesn't depend on wire or anything. It's the properties of electric field and magnetic field. And that's it. There is no wires. I can now draw any surface. I can consider the path, the boundary of any surface, and that must be true. If this is, of course, if that law is correct and it's correct formulation of it, maybe wire plays a role here, but I don't believe it. And so I reformulate it this way, and then I need to check it that this is correct, that there is indeed electric field. Now, it actually tells you quite an interesting story, because it tells you that if magnetic field is not constant in time, right, then the flux is not constant in time, then there must be electric field in the vacuum. So if I take my magnet and I start to change the current through it, so that magnetic field is changing, right, there must appear some electric field in the vacuum. And of course, that's a consequence of it, right? And it can be checked, and it indeed does appear. And that law is correct. Now, again, we have exactly the same problem, but this is a physical law. That's not a theorem of mathematical theorem. It tells you that electric field is connected to magnetic field, right? It's a physical statement of the nature of those fields. But now we still need to consider what happens when we choose another surface with the same boundary, right? And now you can do it easily. What we need to do is to show that this integral does not depend on which surface we take. And it's done exactly the same way. So you consider another surface, right? You write those two fluxes, and you see that it's the difference of the flux from one surface to another surface. And that equals to the total flux of magnetic field through the union of those two surfaces. But the total flux of the magnetic field of the union of two surfaces equals 0. Because now union of two surfaces is a closed surface. So it is 0. And it means that the difference between the fluxes through any two surfaces will be exactly 0. It means that the integral is the same. All right? So this law actually makes sense. It tells you it does not depend on how we choose that surface sigma. Otherwise, we'll have a real big problem. A fundamental law cannot depend on how we choose whatever we want to choose. Does that make sense?
Yeah.
All right. So that's exactly the Faraday's law. So you see that's the Faraday's law. It's a global integral formulation, and of course we can now use that theorem, right, to rewrite the left-hand side as integral over curl of, so that by this theorem equals to curl of E integrated over ds, right, and the same sigma as this one, right? Just instead of A, put E here. And then we see that one integral over sigma equals to another integral over sigma for any sigma, for any surface. So it means that this what's inside the integral here must be equal to the what inside the integral here. And what we have then is the local formulation of the very same Faraday's law, which tells us that the curl of E must be equal to minus dB over dt in any point of space. Does that make sense?
Yeah.
So this is a Faraday's law, right? It looks very different from what I wrote here, right? Epsilon E equals minus dF over dt. But nevertheless, they're completely equivalent to each other. But this one is actually more useful if you consider just the nature of electric and magnetic fields. In particular, because now you see we have time derivative here, right? So we actually now have some dynamics of magnetic and electric field inside our equations. And we can use that equation as one as in addition to those ones. Okay? That makes sense?
Yeah.
It tells me that if I change magnetic field, I get electric field. But it tells me nothing about how do I get magnetic field to begin with. All right, and so there must be another law for it. And what that law is, of course, again should be familiar to you. And it's called Ampere's law. And that Ampere's law in the form which you know is the following: that if you have a current, right, and then you compute the circulation of magnetic field around any loop around the car. So you have some loop, let's call it gamma, right? And you compute the circulation of magnetic field around this loop, right? Then it must be equal to mu naught times the total current. Right? That's probably the form which you're familiar with. And that's how you find what magnetic field is produced by a straight wire. But instead of doing that, instead of writing here the total current, let me do the following. Let me again assume that this is some surface, sigma, and now my gamma is just the boundary of that surface, right? And then I have mu, and here I have the integral over current density dot ds over sigma. Remember that this is exactly the total current which penetrates that loop, that surface. But that we studied current density for basically for this. Okay. So now in this case, what I have here is magnetic field, and the sources for magnetic fields are the current densities. Okay. But now again, it looks good. But now I have to do the same thing, and I need to check whether this integral depends on sigma or not. Right? It tells me that this must be equal to this. This is a physical statement. It's not a theorem. It doesn't tell me for arbitrary field. It says for magnetic field and for current density. So I need to do the same construction here as before. And that's a little bit more involved story here. Let me work this out. And I don't think I need this one anymore, because it will be a little bit longer strain here. So again, let me do exactly the same story as I did before. So let me consider two different surfaces, right? And what I want to check is how this integral depends on the surface. So I have sigma 1 here, and yeah, it's j dot ds. This is for one sigma, and then I consider another sigma with the same boundary, minus integral sigma 1, sigma 2, some other surface, j dot ds. Right. So those are the same integral, but for different surfaces. And I need to see how it how it depends on the surface. Okay, so as the same as before, just switch an orientation of one of the surfaces. I say that this is integral over the closed surface sigma 1 union with sigma 2 of j dot ds, right? Right?
Right.
It's exactly the same as before. It's the same construction. But now what I see here is an integral over the surface, right? According to Gauss' theorem, this must be equal to integral over the volume which is inside the surfaces of the divergence of vector j dv. Right? That's Gauss theorem. Now, but the divergence, but there is continuity equation which tells me that divergence of vector j equals minus d rho over dt. Right? So then what I have here is that I can write here that this is equals to minus d over dt, and here I have rho. Right? Does it make sense?
Yeah.
It's a continuity equation, just instead of divergence of j, I wrote this. It must be correct. Now I go here. And I see that according to Gauss' law, this integral, which is exactly the same integral as there, equals to epsilon naught. So this equals to, oh, where did I write it? Let me write it somewhere here. So this equals to minus epsilon naught. Now I still need to keep the derivative, d over dt, right? And then I have integral over the whole surface, sigma 1 union sigma 2, over electric field dot ds. Right? But now I again take that union of two surfaces and I split them on two surfaces and fix an orientation on them. And what I will have then is exactly, so I will have here integral over sigma 1 plus epsilon naught d over dt integral over sigma 2 e dot ds. Does it make sense? So I see I used a lot of stuff here, right? I use Stokes, I use Gauss theorem, I use Gauss law, and I use the continuity equation. All of those coming together and to produce me that wonderful relationship that this equals to this. And this relation is indeed it's absolutely wonderful because it tells me that depends only on sigma 1, and that depends only on sigma 1 on one of the surfaces, right? This depends only on surface sigma 2, and this depends only on surface sigma 2. So let me then move things around so that everything which depends on sigma 1 on the left-hand side and everything which depends on sigma 2 on the right-hand side. Okay? So what I will have then is the following, that I have here, I need to move this part inside, so it's plus epsilon naught d over dt integral over sigma 1 e ds, the flux of electric field, by the way, right, through my sigma 1, and it must be equal. And what will happen here is exactly the same expression. It's integral over j ds over sigma 2 plus epsilon naught d over dt integral over sigma 2 and flux of the electric field. Okay? Does that make sense?
Yeah.
So what it means is that this expression, the whole expression for sigma 1 is the same as the very same expression for the sigma 2. for any sigma 1 and sigma 2 as long as they have the same boundary. So it means that that expression does not depend on which surface I take. Right? So what it means is, remember that that was my Ampere's law. This one, right? So this integral depends on which sigma I choose. But if I add to it epsilon naught d over dt over sigma e dot ds, then now this expression, that's the whole law, this one, the total one, does not depend which sigma I choose, because the right hand side doesn't depend on which sigma I choose. It's the same for all surfaces. Okay? Does that make sense?
Yeah.
So now you see that it actually didn't change anything which you knew before, because here is time derivative. So if nothing depends on time, you have a constant current going through a wire, right? Then the right hand side will always give you 0. And for everything which you know when it was constant currents, that will be correct. But when currents or whatever electric field starts to depend on time, then electric field which depends on time can be a source of magnetic field, even if there is no current at all. All right? So you see, remember that the Faraday's law told us that a magnetic field which depends on time is a source of electric field. This law tells us that electric field which depends on time is a source of magnetic field. And now I have one more equation, right, which has derivatives of electric field. Okay? So Faraday's law had derivatives of the magnetic field, and now I have also time derivative. And now I have also time derivative of electric field. So this is the correct form of Ampere's law. And by the way, Ampere himself, he only derived this part of it. Right? And he completely missed that one. It was Maxwell who actually did, I think, he actually did the same construction, and he looked at that equation, and he understood that it makes no sense, because the left hand side does not depend which surface you take, depends on the boundary, and the right hand side without the other term does depend on the surface. So there must be something wrong with that equation, because that equation makes no sense. And so he figured out that if you add the following term, that Ampere's law still holds when nothing depends on time. But now the right hand side does not depend on the surface. And by the way, you can actually see it in your standard problem. Remember that the standard problem which you use Ampere's law to solve, it was one wire. It was a wire, right? And you needed to compute what is it has a current I here, and you need to compute the magnetic field around this wire, right? And remember that it would go like around the circles and so forth. Remember those?
Yeah.
All right. Good. But now let me ask you that what you are calculating some sort of circulation of magnetic field around this loop, right? And you're saying that circulation equals to the total current with mu naught, blah blah blah, and then you compute it. But let me ask you the following question: what if I have a capacitor here? Right? So, what's the current? Now, if the current is constant, then, well, capacitor gets charged and that's it. There is no more current, right? But I don't have to rely on that as the current to be constant. What is my current depends on time, like AC current, right? And then capacitor is not a big problem. The current goes back and forth on both ends. So it must produce electric field. But on the other hand, if I take just this law, right, that part without without the second term here. Then what I will have, then I have this surface which goes right in between the capacitor. And there is no, and because it's capacitor, there is no current which penetrates the surface. Right? Electrons do not move in planes, they don't jump around. So then if I try to use this part of the Ampere's law as it was written before, it will be different depending on how I compute the total current. Do I compute total current through this cross section, which has inside the which goes inside the capacitor, or I compute the total current through this cross section, right? Which doesn't have capacitor, so that integral will be zero for the cross section which goes inside the capacitor, and it's not zero which for any other cross section. Right?
Yeah.
But then it means that this law without the term makes no sense whatsoever. If the result depends on how I calculate it, then that's it. It's done with. It makes no sense. And now, if you include this term here, you can actually do that and do the complete calculation. You can compute how electric field, because current goes in, right? It charges the capacitor. The capacitor is that inside the capacitor, then you will have electric field, right? So you compute this integral. This is just a flux of electric field through the capacitor. You take its time derivative, and you will see that it will give exactly the same. This term, for this area, this term will be zero. This term will be not zero. For this surface, this term will be non-zero. This will be zero. And they will work exactly in such a way that give you exactly the same number. And because you know everything about capacitors, you can actually do it, that calculation. You can actually perform it down to the very end, and you will see that it's exactly the same. They have exactly the same contribution. So that's why now right-hand side have exactly does not depend on which surface I choose. I can choose whatever surface I want. But then after I have chosen that surface, I need to figure out what my current density on that surface and what my electric field on the very same surface. And then that integral will not depend on which surface I have chosen. So of course I need to choose the surface which is easier to compute in this case. But well, what's easier for me is not necessarily easier for someone else. All right, so that's the story, right? And again, this is a sort of global integral formulation of it. But now we can use our Stokes theorem here on this part, right? And that what we will have is that curl of B, right, equals mu naught J plus epsilon naught d over dt of electric field. Right? That makes sense?
Yeah.
This is now this simple rewriting of this expression through the Stokes theorem, using the same surface as this one, right? And then you say the surface is arbitrary, so you can get rid of the integrals, and that's what you'll have. So this is the last equation. It's called Ampere's equation or Ampere-Maxwell equation, whatever. Names don't really matter much. And again, it tells you that if you have, you see from here, it's actually quite very visible, right? That if you have electric field which depends on time, then you will produce curl of a magnetic field. So you will have some magnetic field, right? And Faraday's law tells you that exactly the opposite, that if you have magnetic field which depends on time, then you produce curl of electric field. Right? And there's just additional terms that the currents here, which we need to take care of them. Exactly the same way as you have densities of charge in the Gauss law, here we have sort of density of currents in the Ampere's law. All right, so we will continue discussions those, and all of those I will point out next lecture, which will be on Friday, and then we will discuss those equations and what they actually mean. Now, what I want to emphasize right now, is that those equations are not just mathematical peculiarities. Like mathematical peculiarities is just Gauss theorem, Stokes theorem, and so forth. Those equations really describe the world, electric and magnetic fields. Right? Those electric and magnetic fields is what you use. Remember, the light is the electromagnetic wave, and we will get it from those equations. So everything which you see is actually contains in those equations, right? Because the only thing which you actually see is light, and light is contained in all those four equations. Those two Gauss equations, Faraday's law, and this Ampere's law, right? So that's the first thing. The second thing that you all have cell phones or computers. Well, you're supposed to, because you're looking at one right now, and they connect through Wi-Fi probably, right? In all cell network, and all of those are electromagnetic waves, right? So if and it's only possible to have electromagnetic wave and to understand how electromagnetic waves work using those Maxwell equations. And so every time you push a button on whatever computer or telephone, you actually you make an experiment which actually checks the Maxwell equations. So we have like billions and billions of experiments on validity of Maxwell equations, and they are correct, right? So we did check them so thoroughly that it's hard to believe. So I have a couple more minutes. I want to tell you some story about the electromagnetic waves. They were predicted from the Maxwell equations, and people didn't believe them. They thought that the existence of electromagnetic waves means that the Maxwell equations are wrong, because things like that cannot exist. But there was one guy who actually decided to check it experimentally. His name was Hertz. It's exactly the same Hertz which is in your like 60 Hertz in your wall plug, or 50. I don't remember that. A lot of Hertz in there. And so that guy decided to check it, and he made an experiment. So he had one antenna, and about 1 meter away from it was another antenna, and he produced some electromagnetic waves, and he captured them with another antenna, and he showed that they actually do exist, that the energy, the electromagnetic wave can go just through space without any media for them. And so he basically was the first guy who discovered the electromagnetic wave in experiments, produced them and then captured them. And when he was asked what is the practical use for that discovery, this guy who actually discovers them, right? He said that there will be never any use for those things. It's just completely academic curiosity, right? Academic, things. So even the guy who actually invented those electromagnetic waves, he didn't understand what kind of practical use those things can have. Because after that, after his discovery, it took a lot of work by very smart engineers to actually find the use for those fundamental discovery. And now we cannot imagine our world without them. Right? So there is no way to predict which fundamental discovery will be useful later on, because between discovery and use, there is still a lot of work by smart engineers who actually find out that if it would be useful or not. All right, so it's something about science which you need to understand, because that science is never driven by practical use. It's always driven by people's curiosity, and it was curious to see what it is, and then some other smart people come in and found the use. All right, so do you have any questions? Any questions? Am I alone here? All right. Okay, well then, thank you for coming, and I'll see you next on Wednesday we have an exam, and we have next lecture on Friday. Right. Yeah.
Thank you. Thank you.